so my name is Lukas from MachineWare, and today I will talk about early RISC-V software verification with SIM5. All right, let's start. So I first want to introduce you to a methodology that is called virtual prototyping. In virtual prototyping, we use a tool, and this tool is called a virtual platform. A virtual platform is a full system simulator, so you model your entire system, for example, your RISC-V cluster and all your peripheral components such as accelerators, GPUs, etc. in a full system simulation. And this is a very useful tool, and that is much used today for software development and verification. Because today software gets more and more complex every year, basically. You have more complex software, you have more complex hardware. A modern embedded system executes a huge software stack with millions of lines of code that can potentially contain bugs. And full system simulators, virtual platforms, help you to identify these issues even before you have the first silicon of your system back from the fab. There are several advantages of virtual prototypes over physical prototypes. First of all, they can be available much earlier. So if you start your prototype development, your virtual prototype development, while you are also developing your hardware, you can have your virtual prototype even before you have the first silicon back from the fab. And this allows you to shift left your entire software development flow. So you can start your software development, your software verification months before you have your first physical prototype. In addition, since they are simulation, they are very flexible. So you can change things, you can change address mappings, you can change the number of components, you can play with it. And it allows you to also use them a little bit for architecture exploration. And when you have your virtual prototype while you are developing your hardware, also design decisions can be made by trying out the software on your virtual prototype, and that can actually influence your hardware design in a process that we refer to as hardware-software co-design. They allow very deep introspection because they are a simulation. You can press pause anytime and you can zoom in to any detail level that you like, and you can do this in a completely non-intrusive fashion. So in a simulator you have no ticking clocks, and no state changes when the simulator is paused, and that is extremely useful for debugging. And last but not least, and this is also depicted here on the right, they are extremely scalable. So when you have physical prototypes, you have only a handful, only maybe a dozen, and when one breaks, and that will happen, you have just one less. While when you have a virtual prototype, you can copy it as many times as you like. So when you have it ready, you copy it, you can have 1,000 of them running in parallel in the cloud. So with this introduction, I want to come to SIM5. SIM5 is our flagship product, and it is a fast functional RISC-V simulator. That means you take a RISC-V program, for example, an operating system or hypervisor, complete software stack, and you run it on SIM5 on a host machine of a different architecture, for example, an Intel host machine or an ARM host machine. And you run this simulation, and from the simulation you can gather simulation results. And these can be debug information or other things that you can record while you are simulating. The great thing about SIM5 is that it is 2.5 times faster than state-of-the-art simulation solutions. So it's extremely fast, and it allows you to shift left your software development, so you can have better software earlier. Besides performance, there are two other important design goals of SIM5, and that is ease of use. So we want SIM5 to be really easy to use for example, software developers, and we want it to be easy to integrate. Because a lot of people already have a simulation solution and they want to add, for example, RISC-V cores to it, and then they can use SIM5, plug it into their existing environments in an easy way, and I will talk about this some more later on. In RISC-V, customization is a huge topic, and a lot of RISC-V architects want to add custom instructions, custom registers, custom CSRs, and we support this in SIM5. So we have an SDK that is part of SIM5 that allows you to develop extensions for the simulator, and these extensions, they can contain custom instructions, registers, and so forth. And they are automatically loaded by SIM5 during runtime. And this way you can easily also extend the capabilities of the simulator. And you can leverage our just-in-time compilation backend, FTL, for maximum performance. The way in which we envision this should work is you can get a RISC-V reference model from us, which can, for example, run Linux or Android, and then you can use our extension API to add your own custom extension to the simulator in a very easy way. Right. I want to talk a little bit also about interoperability. So I said we want Sim5 to be really easy to use and easy to integrate into existing simulation solutions. So MachineWare CPU models in general, and with this also Sim5, they plug very easily into different existing simulation environments. Of course, we support integration into systemc TLM, which is an IEEE standard for interconnectivity of simulator components. But the downside of standard systemc TLM is that you cannot run multiple cores in parallel, so you cannot easily parallelize the simulation. However, we also have a solution for this with our parallel systemc TLM integration, which allows you, if you have a multi-core RISC-V system, to actually parallelize the execution of the CPU models for maximum performance. We, of course, also plug into other simulation solutions, for example, Synopsys Virtualizer, through an interface that is called OCX. And, of course, we have our own environment, which we call MachineWare Virtual Platform, to integrate into, to build the full system simulation. And if you take Sim5 and plug it into our virtual platform framework, you get a lot of nice things. For example, tool integrations like debuggers, GDB, Lauterbach, MCD, these kind of things. We have a Python scripting solution for continuous integration, and also some trace and analysis capabilities that allow you to record traces during simulation. Also, you can connect easily to protocols such as Ethernet, I2C, CAN. So if you have components that speak these protocols in your system, we can model this quite easily in our environment. With this, I want to introduce the technology that we use to build the MachineWare virtual platforms, which is called VCML. VCML is our virtual components modeling library, and that is actually an open source library. So you can find this on our website, on our GitHub page. And this is a library that allows you to construct full system simulations. So you take the Sim5 CPU model, you embed it into a virtual platform that is based on our VCML library. And this is depicted here on the right-hand side. So you have a virtual platform which contains for orchestration an Accelera system C kernel, and then components, for example, from VCML, such as Sim5, or other peripheral models, such as UART, Ethernet, GPU, these kind of things, or also third-party models, which are systemc TLM compatible. And as I said, in VCML we already have quite a few component models available, which are part of the open source release. So stuff that you always need, like UARTs or Ethernet, things like this are part of our open source release. And all the modeling primitives that you need to build your own peripheral models are also part of the open source release, as are our tool integrations. I want to come to a short demo. And in this demo, I want to show software development with Sim5. So in this demo, we have three windows. One is an IDE. In this case, it is JetBrains CLion, which we use to develop a RISC-V program. We have our simulator console window, and we have our simulator GUI Viper. So IDE, console window, and Viper. And now we are going to start. We are going to launch our simulation, which is just now set up, and it waits for connection from our GUI. So we go to Viper, our GUI for our simulator, which is kind of a cockpit for your simulation, and we connect to our simulation, so to our Sim5 simulation. And now we are ready to run. Now we can go to Viper and look at the state of the simulation. For example, we can look at all the components that are part of the simulator, so CPU models and peripheral models. And we can look at the properties of these models. So for example, we can look at the CPU model, and we can see the register state. We can see all the registers are initialized right now because the simulation has not yet started. We are going to start the simulation. We are going to boot Linux, and you can see the output in our GUI and in the terminal window are the same. And we are logging into Linux, and now we can start our software development. So here in the JetBrains IDE, we use CLion here. We have a RISC-V program that just, for demonstration purposes, multiplies matrices. So we have a matrix A, matrix B, multiply them, and then print both and print the result basically. And right now we have the dimensions of the matrices set to 5 by 5. So it's just a little demonstration, so we compile it now. And after we have compiled the program, we can go back to the simulator and run it on the simulation. So we have a feature in Sim5 that allows you to have shared folders between the host and the simulator. So we put our RISC-V program in the shared folder, we compile it there, and we can directly access it from the simulation and run it. So we go to our shared folder, and then we just run the binary that we just compiled, so our RISC-V project. And you can see, I mean, it multiplies the matrices. But what we can also do now is we can use the Linux perf tool to get some information about the program that we have been running. So we run it using perf, and we can get some cycle counts, we can get page faults, so we model the performance monitoring unit also of the RISC-V core, and we can use it in simulation. Now we are going to change our RISC-V project. So we are going to increase the matrix size, and we are going to compile it again, and then we can run it again. And what I want to demonstrate with this is you can really easily just develop RISC-V software on the simulator, run it, and get insights, for example, through perf on the software that you are developing. And you can see, of course, now because the matrices are bigger, we need more cycles. Also, I just do a cat on proc CPU info to show you we are actually running on a RISC-V system. So it's a 64-bit RISC-V system, and yeah. So the last thing that I want to show you is how you could debug it. So now we can also go to our IDE and make a debug build. And this time I'm going to use the simulator console directly to show you that it's basically the same thing. And we can use GDB to just debug our RISC-V project that we have been developing directly on the simulator. So yeah, we can set breakpoints, we can look at the source code, we can step, we can inspect the register state, we can set watch points. So you can just use it like real hardware, but better. So that's basically it from my side. So I want to end here. But I'm happy if there's time, I can take some questions. Or if you would like to know more about this, please come visit us at our booth. We are right over there, and we can have a little chat too. Thanks.